Good day, grade 10s. Today we are going to talk about electric circuits, which is part of electricity. Part of electricity that we'll be learning in grade 10 is electrostatics and electric circuits. So, for this lesson, we will talk about electric circuits, and then the first part that we will be talking about is the potential difference. Potential difference. This right here. Potential difference, my friends. We'll be talking about potential difference. The definition of potential difference is that it is the work done per unit charge. But if I just read the definition, it won't make sense to you. You see, so I'm gonna lay it out here and try to use some analogies to explain what potential difference actually is, so that you are able to grasp it and understand it well, right? Let me use a scenario. Let me start with a scenario. Okay, so this is the formula. This is the formula of potential difference, right? I'm gonna border it like that, and then I'm gonna use a scenario. So let's say suppose we have a beaker, two equal beakers, right? These beakers, they are the same, and then suppose we have the same amount of water inside these beakers. We have the same amount of water, and the beakers are the same, and then we put a pipe here. This is the pipe, right? We have a pipe, and then this is beaker 1, and this is beaker 2. Now, the water levels are the same, right? So the question is, will water flow? Will the water flow? And then I guess you gave an answer of no, the water can't flow. Why can't the water flow in this pipe? The water cannot flow in this pipe because the level of water inside the beakers is the same, and these beakers, they are at the same height, right? The beakers are at the same height, so the answer is a no. This is because the beakers are at same height, so there is no height difference. That's why the water is not flowing in the pipe. There is no what? There is no height difference. Now, I am going to now lift one of the beakers to a certain height, and the other beaker will remain in the same position, right? So we have the same situation, but the difference now is that one of the beakers is lifted up. So I'm gonna draw beaker 1 is gonna remain in its position, right? And then the water level is still the same, right? So this is beaker 1. But the other beaker, we're gonna lift it to a certain height. So this is the beaker, is lifted up. It's the same, the beakers are the same, right? They are the same, they have the same volume, and then they have the same amount of water, and the level of water is the same. But now the other beaker, we have lifted it up, and then because we have lifted it up, then we make the pipe to actually look like this so that it can connect the other beaker, right? Now we have the same question again, right? So now we have lifted this beaker to a certain height, right? To a certain height. So this is beaker 2. And then we ask the question, will water flow? I guess the answer will be what? The answer will be yes, because of the height. So the water will move here and it will flow because of gravity. It's gonna go down because of gravity, and then it's gonna flow. So there will be a flow of water. The flow of water is caused by what? The flow of water is caused by height difference. Height difference is what is what causes the water to flow, because now there is a height difference, the water that is able to flow. In the first situation, there is no height difference, that's why the water in the pipe is not flowing. But once we lift the other beaker, we create a height difference between the two beakers, and because there is a height difference between the two beakers, the water will flow from the beaker that is higher to the beaker that is lower. Now let's bring this into electricity. Let me ask you a question. If I have a copper wire, like this is the copper wire, and this copper wire doesn't have any battery, will electricity flow? Will electricity flow? So this is a copper wire. Will electricity flow? No, electricity will not flow. Why will electricity not flow? Electricity will not flow because of what? There is no potential difference. So electricity will not flow because there is nothing that is triggering it, right? So electricity will not flow since there is nothing triggering it. Electricity will not flow because there is nothing that is what? There is nothing that is triggering the electricity to flow. But then what happens when I bring a battery? What happens when I bring a battery now? When I bring a battery, so now when I bring a battery, I have the same wire, but now I bring a battery. Look what happens. Now I bring my battery. This is my battery right here, and then we have positive and negative. So now because I've brought my battery, this battery now is gonna create what we call potential difference. That potential difference is what is gonna create the flow of electricity. So now when we bring the cell, then the cell is gonna create a potential difference. So there will be a potential difference. So now because there is a cell, there will be a potential difference. There will be a potential difference because now there is what? Now there is a cell. So electricity will be able to flow. Electrons will now experience potential difference, and then they will be able to move around the circuit. When the wire is alone, the electrons are not experiencing any potential difference, so they are just basically stable, not moving around. So there is no flow of electricity because there's no potential difference. But once we introduce a cell, we create a potential difference. So it means electricity is able to do what? The electricity is able to flow, just like the two beakers, the water pipe in the two beakers. Because of we have lifted the other beaker, water will flow, right? So it means we have created what? A height difference. So when we create height difference, water flows. When we create potential difference in a circuit, electricity flows. That potential difference is created when there is a what? When there is a cell involved in the circuit. So now when there is a cell, there will be potential difference, and that potential difference is what will create the electricity around the cell. And then now we have the potential difference between 2 points in an electric circuit is 17.4 kilovolts. 17.4 kilovolts. 17.4 kilovolts. So this is 17.4 kilovolts. A power source transfers 0.4 megajoules. So the capital M there stands for mega. So it's megajoules of energy when moving a certain amount of charge between these 2 points. Determine the amount of charge that moved between the 2 points. So obviously we want charge. So let me show you a quick way of remembering how to do this calculation. So this is what you must use. You must remember this rectangle. So this will be W, and then this will be V, and this will be Q, right? So if I want to calculate V, then I'm gonna say V is equals to W over Q. If I want to calculate Q, I'm gonna say what? Q is equals to V over W. If I want to calculate Q, I'm gonna say W over V, because V is at the bottom, right? If I want to calculate W, I'm gonna say what? W is equals to V times Q, because both V and Q are at the bottom. So that's how you remember. In this question, we are looking for what? We are looking for charge. We want to calculate charge. It means we're gonna say what? We're gonna say charge is equals to what? So this is the charge, right? Charge is equals to W over V. So W over V. Charge is equals to W over V. And then we have W. We have to write W. W is given as 17 point. Sorry, it's given as 0.4. W is given as 0.4. So W is 0.4 megajoules. But the capital M, it stands for 10 to the power 6. So the mega means 10 to the power 6. So if you remember the first lesson where you learned about gigs, and you learned about mega, gig, peka, micro, milli, kilo, etc. So this is where you learn about this nano, etc. and others. So the capital M, which is mega, the capital M stands for mega. It means 10 to the power 6. So if you do 0.4 times 10 to the power 6, you're gonna have 400,000 joules. You'll get 400,000 joules. And then V is given as 17.4 kilovolts. We're gonna change it into volts, right? We have to make sure that the units are in their SI units. So then V, we're gonna write it as 17.4 kV. The K means kilo. It stands for 10 to the power 3. And then we're gonna have V is equals to 17.4 times 10 to the power 3 volts. And then we have V is equals to 17.4 times 10 to the power 3 is 17400 volts, 17,400 volts. And then now when we substitute, we have 400,000 joules divided by 17,400 volts and then when we do the calculation we will get 22.99 coulombs, which is approximately 23 coulombs. It's approximately 23 coulombs, right? So this is how we do the calculation. So this is the amount of charge that moved between the 2 points. So this is the amount of charge that moved between the 2 points. And then next we now have voltmeter. So voltmeter is an instrument for measuring, it's used for measuring the potential difference between 2 points in an electric circuit. So you can see here you can have this, right? And then you have point A and then you have point B. So here you have points A and B. So the voltmeter is used to measure the potential difference between 2 points in a circuit. So those can be the points. You can have point A or point B. And then this potential difference, we can talk about what we call high potential and low potential. So when you have electrons, when you have negative charges this side and then you have positive charges, for example this side, right? If I have an electron here, this is an electron, right? Or I will call it a charge. It's an electron or a charge, it doesn't matter. So this charge here, right, when it is near the negative side, it is at a high potential, so it's experiencing a high potential energy. And this, the reason why it's experiencing high potential energy is because it's being repelled, it's closer to the negative, so it's experiencing repulsion. It's experiencing a lot of repulsion. So because it's experiencing repulsion here, this charge is going to be pushed by these negative charges right here. So it's going to be repelled, right? Repelled. As it is repelled, it's going to be attracted to these positive charges until it reaches this point where it now rests near the positive charges, right? Once it reaches a point where it is now resting near the positive charges, it is now at a low potential energy. So this section is going to be its lowest point. So it is at a low potential energy when it is now near the positive charge. And when it is near the negative charge, it is at a high potential energy. So now it is at a low potential energy. So this is how you see that, yeah, this is what happens basically. And then the movement from one point to the next we measure is what we call basically the potential difference. The potential difference is actually the difference between the points at which the charge moved. That's why it's called the work done per unit of charge. That's what the definition of potential energy is called, the work done per unit of charge. So when we write the formula, potential difference, which is V, right, between 2 points. So between 2 points is equals to work done, which is W, over per unit of charge, which is Q. And then we know that V, the units are capital V, and then for charge the units is Q, coulombs, which is C, and then we know W, the units is joules. is joules. And then here we have an example. A battery does 1440 joules of work. So we have 1440 joules of work when moving 480 coulombs of charge from one point to another in an electric circuit. What is the voltage across these 2 points? So we have this, we can draw a wire where we have point A and we have point B, right? So we see that the battery does a work of 1440 joules to move a charge from one point to the next, right? So the charge is moving from one point to the next, and then the work done to do that is 1440 joules, and then the charge that was moved is actually 480 coulombs. So to find the voltage across the 2 points, so the voltage across these 2 points, we can just say V is equals to W over Q, and then we have 1440 joules over 480 coulombs. And then when we do the calculation, we will get 3 volts, because we are calculating volts, so the answer must be in the units of voltage. So this will be 3 volts. And then now let's talk about EMF. Now EMF, when we talk about EMF, we have a battery in an incomplete circuit. So you can see here the battery is connected, right? The voltmeter is connected to a circuit that is not complete, right? So this is an incomplete circuit. This is an incomplete circuit, as you can see. So we can see this is the cell or the battery, right? So what is happening here? So the EMF, so before we talk about that, when you measure the potential difference across or between the terminals of a battery that is not in a complete circuit, like this circuit here that we have here, you are measuring the EMF of the battery. This is the maximum amount of work per coulomb of charge the battery can do to drive charge from one terminal through the circuit to the other terminal. So when we measure the potential difference across the battery, when the battery is connected to a circuit that is not complete, like this one, we are basically measuring the EMF. We are measuring the EMF, and the definition of the EMF is here, is that the EMF, this is the definition of the EMF. Let me highlight it for you. So this here is the definition of the EMF. It is the maximum EMF definition. It is the maximum amount of work per coulomb of charge the battery can do to drive charge from one terminal through the circuit to the other terminal, right? And then you can see here we have an image of a scientist. This scientist is called Alessandro Volta, and the unit of volts was named after him. He was an Italian physicist and chemist who is best known as the inventor of the first true electric battery. The first true electric battery was invented by Alessandro Volta, an invention that laid the foundation for modern electrical science. The SI unit of the electric potential, the volt V, is named in his honor, recognizing his fundamental contributions to the science of electricity. So he did a lot of contribution to the science of electricity. Yeah, so when the circuit is incomplete, we are measuring the EMF. So don't forget that. It's very, 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 very important to remember that, so that you are able to know how to deal with problems and questions that ask relating to that. Because once you understand what EMF is, then you'll be able to understand the whole electricity and be able to grasp a lot of concepts. And then now the circuit is complete. Now we are dealing with a complete circuit, right? So the electrical potential difference is also called voltage. That's another name for it, right? When you measure, so another word for potential difference is voltage. When you measure the potential difference across or between the terminals of a battery that is in a complete circuit, now the circuit is complete, right? You are measuring the terminal potential difference of the battery. Although this is measured in volts, it is not identical to the EMF. So terminal potential difference, and EMF are measured in volts, but they are not the same. They are not the same. Very important. So in this case, what we are measuring here, we are measuring what? We are measuring the terminal potential difference of the battery, because now we are measuring the battery that is connected to a circuit that is what? A circuit that is complete, right? Yeah, so it's very important to note that. So when we have a circuit that is complete, and then we are measuring the voltage across the battery, the reading we are gonna get is what we call the terminal potential difference. But when we measure the voltage across a battery where the battery is in a circuit that is incomplete, we are measuring the EMF. So do not forget that. It's very important to actually remember that. It's very important to make sure that you remember that, right? Yeah, you remember that. So when we have this situation where we have a battery, and then we measure the voltage, and then the circuit is incomplete like this one, you have a cell here. So in this case, what we are measuring is just the what? Is just the EMF, because of we are measuring in an incomplete circuit. So we are measuring the EMF in this case. And then we have current, the flow of charge. So when we talk about current, we talk about how much charge moves past a fixed point in 1 second. Think of charges being pushed around the circuit by the battery. There are charges in the wires, but unless there is a battery, they won't move. So in this case, you can think of this as a wire, and then the marbles, they represent what? They represent charges. So these charges, they move towards this direction, and they push each other or influence each other, and the flow of those charges is what we call electricity. When one charge moves past the next to it will also move. They keep their spacing as if you had a tube of marbles like in this picture, or looked at a train and its carriages, right? So if you push one marble into the tube, one must come out of the other side. As you can see, if a train locomotive moves, all the carriages move immediately because they are connected. This is similar to charges in the wires of a circuit. The idea is that if a battery started to drive charge in a circuit, all charges start moving instantaneously. Instantaneously just means immediately or with immediate effect. This is the picture of Benjamin Franklin. As you can see, this is Benjamin Franklin. Yeah, he appears on dollar, American currency or American dollar bills. Yeah, he was a scientist. He was a scientist. He was a scientist. Yeah, who did research in electricity. Benjamin Franklin made a guess about the direction of charge flow when rubbing smooth wax with rough wool. He thought that charges flowed from the wax from positive to negative, which was opposite to the real direction. Due to this, electrons are said to have negative charge, and so objects which Ben Franklin called negative, meaning a shortage of charge, really have excess of electrons. By the time the true definition of by the time the true direction of electric flow was discovered, the convention of positive and negative had already been so well accepted in the scientific world that no effort was made to change it. So, uh, what was commonly taken as a belief was that electrons or charges, they move from positive to negative, right, in a circuit. But they later discovered that that is not true. But this, because of it stood for many years, they ended up letting this be, right? And then this that they just allowed, that electrons or charges move from positive to negative, is what became known as the conventional current, the conventional direction, or the conventional current. That's what became known as the conventional current. And then now we have a copper wire. This is the image of a copper wire, as you can see there. A current is defined as the rate at which charges moves past a fixed point in a circuit. The units of current are amperes, which is defined as 1 coulomb per second. So it's defined as 1 coulomb per second. It comes from this, where current is equals to Q over delta T, and then we know the units of current is amperes, so we can say 1 amperes, and then here we have 1 coulomb over 1 second, and then amperes is gonna equals to C over S, which means that amperes is actually coulombs per second. So coulombs per second. And then now let's talk about let me draw a circuit so that we can talk about something very important. So let's say we have a circuit, and then this is the battery, and then this is the positive side, this is the negative side of the battery. then this is my battery, and then I have a bulb here, right? Now electrons are negatively charged, we all agree on that. So electrons are negatively charged. Now these electrons, because they are negatively charged, they will move away from the negative side of the battery. So they will move away from the negative side of the battery, and then they will flow away, and then they will move towards the positive side of the battery. So they are moving towards the positive side of the battery, these electrons. Then they will continue moving towards the positive side of the battery because they are negatively charged. So they are repelled from the negative terminal of the battery. So the electrons are repelled. Negative terminal of the battery, and then they are attracted towards the positive terminal of the battery. And then they will continue to move and be attracted towards the positive terminal of the battery. So you can see that the direction of the electrons is actually showing you that the electricity is moving in this direction, right? So it's moving from negative to positive. So in reality, the electrons flow from negative to positive in reality. But in circuit analysis, when we analyze circuits and we do calculations, right, we use the conventional current, which says positive, which says direction, the direction of current is from positive to negative. So we use this conventional current to do calculations, and it works well, right? But this that I showed you here is I wanted you to understand that the real direction of electric flow is this, and the reason why it's like this is because of electrons are repelled from the negative side, and then they are attracted towards the positive side. So you'll have this direction of current. But when you do calculations in circuit analysis, what we use is the conventional current, right? The conventional current says that current moves from positive to negative, positive terminal to the negative terminal. So that is the conventional current. So that means if I have a circuit here, and then the same circuit, and then we know this is the battery and this is the positive, this is the negative, the direction of the conventional current is gonna go from what? From positive to negative. So it means the direction of the conventional current is gonna look like this. So this is the conventional current. So this is the conventional current. And then we have a plasma ball. A plasma ball. So that's the picture of a plasma ball, but we will talk about it. We'll talk about a plasma ball as we are discussing. So we use the symbol I to show current. So as you can see here, the symbol I, it stands for current, right? And then it's measured in amperes. 1 ampere is 1 coulomb of charge in 1 second. We have shown that. This part we have shown, right? And then when current, so this is the equation. When current flows in a second, we show this on a diagram by adding arrows. The arrows show the direction of flow in a second. By convention, now you can see by convention, we say that charge flows from the positive terminal or on a battery to the negative terminal by convention. So this is what is used in circuit analysis when we do calculations. This is the direction that we use, that charges are moving from what, from positive to negative. If the voltage is high enough, current can be driven through almost anything. That's amazing, because it means that we can actually drive current through water if it's high enough. So if the voltage is high enough, current can be driven through almost anything. So we can even drive current through water as long as we have enough voltage to do that. In the plasma ball example on the left, the plasma ball you can see on the picture, a voltage is created that is high enough to get charge to flow through a gas in the ball. So the voltage is very high, but the resulting current is what? Is very low. So this makes it safe to touch, even though the voltage is very high. But still you are able to touch it because it won't affect you that much, right? And then the units, we have spoken about them. So if you check the equation Q over delta T, Q we saw that is measured in coulombs, and then delta T is measured in seconds, right? And then I we saw that is measured in amperes. And then we have an ammeter. An ammeter is used to measure the flow of electric current in a wire, right? So an ammeter is an instrument that is used to measure the rate of flow of electric current. As you can see here, the rate of flow of electric current in a circuit. Since one is interested in measuring current flowing through the circuit component, the ammeter must be connected in series with the measured circuit component. So the ammeter is always connected in series with the measured circuit component. So whatever that we might want to measure, we must make sure that we connect it to the ammeter in series. So if we want to measure for example, this will be the ammeter. We want to measure the current flowing through the bulb, for example. It means we must make sure that the ammeter is in series with the bulb, right? So it's very important to remember that. And then here is the picture of the ammeter, as you can see it, right? So the ammeter must be in series in order to be able to measure whatever current that is flowing through that wire. Very important to remember that. And then as you can see here, the arrow shows us the direction of what? It shows us the direction of the conventional current, which moves from positive to negative. So the direction of the conventional current is that it moves from positive to negative. Very important to remember that. Don't forget that. It's very, very, very important. So you must never forget that is the direction of the conventional current, as you can see. And then we have different components of the circuit. You can see the symbol for the light bulb. It's given here. Then we have the symbol for the battery. and then we have the switch. We have the symbol for the battery, and then the big, this long vertical line represents positive, and then the shorter one represents what? It represents negative. So, and then we have the symbol for the switch there, and then we have the symbol for the resistor. Or we also have voltmeter, and then we also have voltmeter, we have ammeter, and then we have the connecting lead, and then resistor. There are two symbols for resistor. You can either have this or you can have this. So there are two symbols for resistor. So instead of using the other symbol, they can use the other symbol. Or also when you draw the circuit, you can choose to use the other symbol. So the other, it shows you that when electrical current reaches this place, or the electrons, when they reach this place, they are actually taking longer to pass through, right? That's what it tells you. That's what the symbol tells you basically. So as you can see, the V, which is voltmeter, it measures the potential difference. The ammeter measures the current in the circuit, and then the connecting lead connects the circuit elements together, and then the switch allows the circuit to be open or closed. A battery does not produce the same amount of current no matter what is connected to it, right? While the voltage produced by a battery is constant, the amount of current supplied depends on what is in the circuit, right? So what is in the circuit determines the amount of current being supplied. It's very important to remember that the amount of current being supplied depends on what is in the circuit. Very, very, very important. That's why it tells you that a battery does not produce the same amount of current no matter what is connected to it. While the voltage produced by a battery is constant, the amount of current supplied depends on what is in the circuit. So it means if a circuit contains more things, you are likely to have low current, right? Yes. So it depends on what is in the circuit. So it will determine the amount of current that is going to be supplied. So it's very important to remember that. And then we have instrument, the voltmeter, which measures voltage. So you can see that the voltmeter measures voltage, and the ammeter measures the current, right? And then now we have these few examples here. The first one says an amount of charge 45 coulombs moves past the point in 1 second. What is the current in the circuit? So the charge, we can assume it moves, let's say, from point A to point B, and it moves from this, the charge is 45 coulombs, and it takes what time? It takes delta t is equals to 1 second to move from point A to point B. So we want to find what? The current in the circuit. So to find the current, then we just say current is equal to t, and then the charge is equal to t, and delta t is 1 second, and then when you do the calculation, we'll find 45 amperes. So that would be the charge. And the second example says an amount of charge equals to 53 coulombs moves past the fixed point in a circuit in 2 seconds. Now an amount of charge equals to 53 coulombs moves past the fixed point in a circuit in 2 seconds. What is the current in the circuit? So the same thing, we have I equals to Q over delta T, and then we have the charge is 53 coulombs over 2 seconds. And then when we do the calculation, we know that 52 divided by 2 is what? Is 26. So it means this must 53 divided by 2 must be 26.5. So the answer must be 26.5 amperes. And then we are told that 95 electrons move past a fixed point in a circuit in 1/10 of a second. In 1/10 of a second, what is the current in the circuit? Each electron carries a charge of 1.6 times 10 to the negative 19 coulombs. So 95 electrons move past a fixed point in a circuit in 1/10 of a second. What is the current in the circuit? So we know that one electron has a charge of 1.6 times 10 to the negative 19 coulombs. So the total charge is going to be what? It's going to be 95 times 1.6 times 10 to the negative 19. So this will be the total charge. So this will be the total charge. So we can calculate this total charge, 95 multiplied by 1.6 times 10 to the negative 19. And then we get an answer of 1.52 times 10 to the negative 17 coulombs. And then we are also told the time. We are told that this happens in delta t is equals to 1/10 of a second. So 1/10 of a second means 1/10 seconds. So this is 1/10 of a second. And then we want to calculate the current. So we're going to use the formula I is equals to Q over delta T. And then 1/10 of a second is the same as what? Is the same as 0.1. So it's basically 0.1 second. And then when we put these things in a calculator, we're gonna have what? We're gonna have a charge is 1.52 times 10 to the negative 17 coulombs over 0.1 second. Then we can punch this on a calculator. And then when we punch them on a calculator, we have 1.52 times 10 to the negative 17 divided by 0.1, and then we'll get a electrical current of 1.52 times 10 to the negative 16 amperes. So it means the current is 1.52 times 10 to the negative 16 amperes.